hold on. I think I messed that up a bit. Alright, good evening, good day, good morning, whatever, wherever you are in the world. Okay, hold on. I think I messed that up a bit. Hold on. I think I know where I messed up. Alright, good evening, good day, good morning. Who is playing? I see. My YouTube channel, the YouTube stream is playing in the background here. Okay, let me just close that first. Alright. I hope the audio is not feeding back anymore. I see people on the chat again. For those who are not part of this group, these are my students. Hi, guys. Specifically, these are the younger students. Oh, it's black. Hold on. All right, there we go. Can you hear me now? Hope you can. Can you see me now as well? Hi, guys. All right. So again, for those who are joining who are not in this group, basically, or for anyone who would like to watch this later, not live, welcome. And this is a special stream. This is just gonna be a 30-minute stream, because some of my grade 12 students are asking for quick explanation on something. You guys, those who I can see here, I see you guys are very supportive. Thank you. All right, who am I teaching? Uh, again, Jackie, yeah, I see your message here. I am teaching no one today. I'm just gonna make a special stream for the grade 12 students. If you want to watch along and learn something, go ahead. Yeah. Okay. All right. So let's start. Okay. So hold on. Let me just get something ready here. I think. Okay. Let me just finish this up. Well, I hope you do. Director, whoever you are, I'm not sure who you are. So director, thank you. I hope you do later on. But this is going to be relevant for you partially in grade 9 when you're doing chemistry, and when you get in grade 10, when you'll be doing physics. Okay. Of course, it's still never too early to learn something as long as it's explained well. So hopefully that I can do that for you today. All right, so let's go on to the 30-minute lesson for today. Okay, so I am looking forward to some of the grade 9. Oh, director is Kiana. Okay, thanks, Arya. All right, so I'm looking forward to seeing some of the grade 12 students here, but if they don't appear, it's fine. They can just watch the stream later. All right, so anyway, it's time to learn. All right, so first of all, today's topic is atomic structure, specifically the gold foil experiment. All right, so where is my resource stuff here? All right, okay, so first of all, when we say atomic structure, one of the first things that usually comes to mind when it comes to atomic structure is this particular thing. Okay, I'm gonna copy and paste that here. Most of the time, you will see that an atom in diagram form looks like that. It's got something in the middle and it's surrounded by all these things, and these things seem to be going around in circles, and those circles sort of intersect. Okay, now I'm going to tell you this much, that this model is an outdated version. This is the most popular one you would see in textbooks, in science videos. These things, some of them acknowledge the fact that I'm telling you that this is an outdated model. So, for you to know what the outdated model is, you need to know what the actual history of the models are for the atomic structure. Okay, so here, here's a bit of history. I'm not gonna dwell too long on here. So I'm just gonna say that this is the history of atomic models. Okay, there is one more atomic model. Some grade 9, you already did this. I just remembered. You already did this like last term, if I'm not mistaken, or last semester, definitely, right? So those in the stream, you're mostly grade 8 students of mine. So you've seen this before. Yeah, we did. I'm looking at the chat now. Yeah. Yeah, we did, right? Again, I'm just discussing this as a bit of an introduction to the actual topic. Okay. All right. So what exactly is happening here? Hold on. That's just a bit weird. Okay, there we go. Okay, there. So the atomic model, we know what this is. This is Dalton's model. Oops, I'll change my pen to a thicker one. Okay, so this is Dalton. Okay, and this one is the second one is anyone on the chat who kind of recognizes this, you can just say what the answer is. If you don't want to say it, it's fine. This one is the Thomson model. No P Thomson. Okay. Then the next one is the anyone remember? If not, again, this is the Rutherford model. Okay. The next one is the Bohr model. And the last one is the Schrodinger or the electron cloud model. Uh, Schrodinger. Okay. And oh, guys, thank you. You've just given me an achievement in the streaming app here. You gave me 100 messages today from the chat. Thank you, guys. Yeah. It's I know it's not really like it's not really like a real award, but it still feels nice to get that. Thank you. All right, let's continue. All right, so the fact here is there's a lot of things that you've learned before about these different models, right? What we're gonna focus on today is this: the contrast between the Thomson and the Rutherford model. Okay, Okay, so what exactly is happening here? How did we shift from the Thomson model to the Rutherford model? Okay, let's take a look first at what the Rutherford model is close up. Okay, or sorry, the Thomson model first. As we all know, the Thomson model, or for those in the chat at least, you know this already. The Thomson model is basically you have a sphere. So let me write that there. Okay. The Thomson model, which is also called the plum pudding model, right? Okay. The plum pudding or the Thomson model, um, the idea here is that your atom, this is your atom, and your atom is a big positively charged sphere. Plus charge, I'll type it, I'll write it in. Big positively charged sphere. Okay, I'll put sphere here. Sphere that is Okay, and then at this point in time, we have discovered, or Thomson has discovered electrons. So what he proposed was these electrons were placed all over the atom like this in random positions, like the raisins or the pudding, or the raisins or the plums in the plum pudding. Okay, so these are the electrons. Okay, now another recap here for the Bohr model. No, sorry, not the Bohr model, the Rutherford model. Okay, this is also called the what? Planetary model. Okay. Uh, what's important here in the planetary model? For again those in grade 8, you've learned this before. The planetary model is you have a nucleus, and it's positively charged, and then you have the electrons going around the atom like this. So these are the electrons, right? Now, Of course, when there's a new model, that means the old model is outdated. There's something that it cannot explain. Okay, so that's always what you think about whenever there's a new model. A new model will always explain a new discovery better than an old model. Okay, so you keep this in mind, and this is always why we need to keep coming up with new models every so often, because sometimes we discover something that the old model cannot explain. Okay, I'll give you an example here. What is it that the old model of uh, the plum pudding model cannot explain here? Hold on, let me just do this quick typo change here. All right. So, so the question now is, what was the old model's flaw? Okay. All right. Flaw. Okay. Anyone from grade 8 or sorry, anyone from grade 12 here from my students? Just say hi. So at least I can see. Okay. I think it's only you guys from grade 8 that I see. All right. So anyway, let me just go back to the chat. All right. But it's fine. Okay. Now the key idea here is that at this point, this is something you guys in chat, the ones that I'm familiar with, you haven't learned this particular bit yet. Well, not in class anyway. If you've learned it somewhere else, that's great, right? But the idea here is that so this is a bit of a preview, okay? So the um, before the Rutherford model, okay, alpha particles have been discovered, okay, were discovered, okay. Okay, the problem with alpha particles then is that we don't really, at the time, they didn't really know what they were. So they just called it alpha particles, okay? So at the time, they didn't know what it was or what they were. We didn't know what they were. All we knew was their properties, okay? All we knew at that time were the properties. So known properties were what? Known properties, they were large. By atomic standards, they were large. Okay, how large? They are about as massive as some of the lighter nuclei that we know, like hydrogen, helium, lithium. Alpha particles have large masses. Okay, you would expect subatomic particles to have tiny masses, right? Radioactivity was also part of it, but alpha particles themselves are not radioactive. Okay, so Arya, thank you for saying that, but at least you learned something new, right? Learning coding, who's that? Okay, so anyway, while we're waiting for that, known properties, they were large and they were positively charged. Okay, I see here that Arya also, director also said more kinetic energy. Yeah, kind of, but that's because of the large mass. Okay, okay, all right. So again, the known properties of alpha particles is they were large and positively charged. So before we continue, let's kind of think about it like this. If something is large, is it easy to move? Specifically, let's not just say large in terms of let's just oh hi Brandon. Is that you, Brandon, from grade 12? Think so. All right. So anyway, The idea here is this: it's if it's big when it comes to mass, if it's big, it's not easy to move, right? So if you try to push the best comparison I can think of right now is a truck versus a toy truck. The toy truck doesn't need a lot of force to get it moving, right? Well, director, energy doesn't really. Okay, I'll just address that. Having a lot of energy doesn't mean it's hard to move or hard to change moving. It's still easy to move, depending on. Let's just think about it. If you have the small truck, if you have the small truck and you have the big truck, and they're of equal mass, it's gonna be both easy to move, right? But if the big truck really had more mass and the small truck and the toy truck has just a small mass, the small toy truck should be easier to move. And it also means that if they're already moving, it should be hard to stop them. So that's the basic idea. And always the basic ideas are the best places to start, right? So the smaller the mass, the easier it is to move. And conversely, the smaller the mass, the easier it is to change its motion. Hi, okay. Oh, it's Fugo. Hi, thanks for watching. I hope this is helpful for your son. Okay. All right. All right. So anyway, that's the key idea. A large mass is harder to change its motion. All right. So again, okay then. So it's harder to change the motion of a less massive object than it is to change the motion of a large object. Okay. Now, one more thing that we probably know is charge. If something is positive and something is positively charged and you put them together, what happens? Again, positive, guys, I'm seeing something. Please be nice. Brian, I told you before in a stream, please be nice. Right? So positive and positive will repel. Negative and negative will also repel. Okay? If you have positive and negative, they will attract. So keep those two things in mind as we go to the explanation. Okay, we're now going back to the board. Now, let's compare the Rutherford model. I'm going to put the Rutherford model here on the right, and we're comparing it to the Thomson model here on the left. And let's say that the positive charge, okay, Lionel, thank you for that comment. Yeah, it's like a magnet. North and north repel, south and south repel, north and south attract, right? So anyway, going back here, I'm going to put the atom here, similarly sized atoms. And let's say that the charge of this whole thing is, I'm going to make it easier, gold. If we look in the periodic table, gold has an atomic number. I have forgotten what it is. I'm going to go check the periodic table real quick. Periodic table, gold, AU has an atomic number of 79. Okay. All right. So 79. So this would have a charge of plus 79, right? And this would also have a charge of plus 79. This is what we know now, and we're going to implement what we know now and see and compare what's happening, okay? Now, the idea here is that the Thomson model, this plus 79 here, is, there's also 79 electrons in here, okay? So same thing here, there are 79 electrons, okay? All right. So the problem is, not the problem, the difference is, for the Rutherford model, we now know that all those 79 positive charges are in the nucleus. But here, these 79 are like distributed all over the sphere, right? So what I'm gonna do is, I'm not gonna do this with 79 positive charges. I'm just gonna make this with with 5. You know what? I'll make it 6. So I'm gonna make it with 6 pieces like that. right? So each of these 6 pieces would have a positive charge of 1. So you can just imagine that these are 79 pieces of positive charges, but they're distributed all over the sphere. At the same time, you have your negative charges. So your negative charges here are also here. They're like here and here, here and here, here and here, right? But we know that our 79 electrons are going to be outside in the Rutherford model. So I'm just going to draw the 6 electrons here again. Okay. Now, Arya, I see that comment. The nucleus must be so dense. Yes, it is. Okay. Just to give you an idea, how dense is the nucleus? If everything was as dense as the nucleus, uh, I don't know the exact number, but I'm gonna guess it from what I know with about stars. Okay. If everything was as dense as the nucleus, something as big as this stick, this whole stick, would weigh like 100 million tons. That's again just from memory. I'm not sure how accurate that statement is, but that's what I remember. Okay. So basically, this is why we're kind of thankful, if you think about it, that there's a lot of space between the nucleus and the electrons. Okay. So going back to the point. So remember what we said about alpha particles. Alpha particles are big and positively charged. So what I'm going to do now is I'm going to draw just a couple of alpha particles streaming like that. Whoop, I'm not going to make it go all the way yet. Just here. Like that. So some of them will basically, you know what, I'll just do 3. Okay. All right. Because of the fact, look here, I'm going to zoom in real quick here before we move on. So if you think about this, each of these little sections has a total charge of 0. Total charge of 0. So if the total charge is 0, what is this alpha particle gonna do? It's not gonna be repelled. It's not gonna be attracted. It's just going to go straight through. So that happens. This happens and this happens. Go straight through. Okay. And this is what Rutherford expected. So let's go back to normal zoom. So this is again Rutherford's expectation. Oops. This is Rutherford's expectation. Okay. But when he, so basically what he did was, now one more thing before we continue. Um, One more thing before we continue. Rutherford did this experiment to prove the Thomson model. That's weird, isn't it? He didn't set out to prove that the Thomson model was wrong. He wanted to prove that the Thomson model was right. But let's go now to what Rutherford actually observed. So again, this is let's make this go like this, same thing. Oh, sorry, not all the way there. Let's do it one more bit. Here, here, and here. Okay. All right. So, hey, I see it in the chat. Okay, again, you guys, Jackie, Arya, you know you guys. Yes. Hugo. Is that Hugo? Okay. Yeah, these people are from Jakarta. I'm actually based in Jakarta myself. So these are actually my students in school, so they're here to support the stream. So again, thank you guys. And you, thank you for joining the stream. I think this is my this is my first live non-student audience, so to speak. All right. So going back. So remember that this is a positive charge. These alpha particles are positively charged. This is going quite far from the nucleus. This first one's quite far from the nucleus, right? So what's going to happen? It's going to be attracted by the electrons, okay, and going to be repelled by the nucleus. But because of the difference in distance, basically, think about it this way. This thing will be repelled. I'll just write it here. Repelled by a few electrons, but sorry, not repelled. This is attracted, right? Attracted, and then this is repelled by all those 79 protons. By 79 protons, right? So I'll just undo everything here so far. So what's gonna happen? A few electrons versus those all those protons. The protons win, right? So since the protons win, what's gonna happen? This alpha particle, the one on top, will be repelled. So it looks like it bounces off, which still is okay because if we add some more particles here, there is a chance here where if you do that, you'd actually meet a proton, a positive charge, but not the electron. So you could still expect a little bit of that, right? But here is the surprise that Rutherford got. This one here. In this case, we know it's gonna head straight into the nucleus. What happens? Nothing attracts it anymore because it's heading right into the nucleus. It's gonna be entirely repelled, right? So what's gonna happen? Two things could happen. It depends basically on how close you get to the nucleus. Either this happens or this happens. Either one of these is a large deflection. And this, everyone, is what is, for those who may have read about this is the surprise that Rutherford got. This was actually a surprise. Okay. And then that's when that's when he realized the Thomson model was wrong. He had just discovered the true nature of the atom, at least up to that time, the true nature of the nucleus, to be more specific. Okay, so for the grade 8 students, this is already, if you haven't learned this yet, this is the level of understanding that I would expect from you. Okay, I'm going to go a bit deeper now and go into how I would explain this to a grade 11 or grade 12 student. Okay. All right. All right. But I just want to ask you guys, is this clear so far? Luis, do your presentation. You have it tomorrow. Okay. Hi, Dior. I see you. Uh, yeah, I see that message. But you all get it, right? Grade 8, grade 12. Anyone else who's watching, you all get it, I hope. Right? You're all saying yes. Great. Okay, grade 12 students, if you're here or if you're watching later, this is where we go into deeper territory. Okay, so the Rutherford model, Rutherford did a few more experiments. Okay, all right. Okay, what was it still basically involved bombarding gold foil with alpha particles. Oh, before we go there, why gold? I forgot that before we go there. Why gold? Why not silver? Why not iron? Why not any other metal? Of course, you can understand why not the gaseous elements, right? It has to be a metal, but why gold? The main reason here is the properties of gold. Gold is the most malleable element or most malleable metal. For those, anyone remember what malleable means? Okay, malleable is what? Director Gold can make us rich. Yep, yep. Okay. Okay. Gianluigi, can I call you Luigi for now? Yeah. Yeah, most of these guys are again from Jakarta, from Indonesia. Most of these guys are my students in class. They're here to support the stream. So for those who are not there yet or are not here and are watching the stream for the first time, thank you. Welcome. Okay. All right. So going back. So malleable means what? Anyone? I'll just go straight here. Okay. Malleable means it can be hammered very thinly into sheets. So hammered into sheets. Okay. Now, most metals are malleable. Most, not all. However, gold is the most malleable because gold has this particular ability to be hammered into sheets that are actually 1 atom thick. 1 atom thick. So it makes it ideal for the gold foil experiment. Okay. New record, 18 viewers again. And we just started, so new record of 18 is nice. Thank you. All right, going back. So, okay. All right, so where was I? Okay, grade 12 territory. We're now gonna go into the strong force. Lionel, yeah, that's also the reason why it's edible because you don't really need a lot of gold to cover food, but that makes the gold covered food really expensive, right? Right, exactly. So going back, so we're gonna go into the strong nuclear force now. So for the other students here, if you'd like to keep listening, go ahead. Strong force. Okay. Now, what do we know about the strong nuclear force? I'll add the word nuclear here. Aside from the fact that it's strong, okay, we know that the strong nuclear force is two things. It's very strong. It's the strongest force there is in the universe. Okay. And we also know that this is very short-ranged. Okay. Now, I'm just gonna, yeah, random guy, the gold food. In my opinion, it's not really a scam in terms of you are getting gold. I don't agree with you on that bit, but I agree with you on the fact that, eating gold is should be done. I don't think it should be done. It's just a status symbol in my opinion. All right, so where was I? Okay, so I'm just gonna look for something here. Uh, Properties. Okay, I'm just gonna go get a table from the internet. I usually quote things here, but I want to look for something that, yeah, okay, this one. All right, we've grade 12 students, you've seen this particular table before, and I'm just gonna copy that from the internet. Sorry, source. I will quote you later on the comments, or rather on the descriptions. Okay. So for the source, I'll get back to you soon. Copy image. All right. Let's make it easy and fast. So basically, again, grade 12 students, you've seen this table. Okay. This is relative. This part is relative to strong nuclear force. If the strong nuclear force has a strength of 1, gravity has a strength of 6 to the 10 to the 39, negative 39. In other words, the strong nuclear force is, what's 39 zeros? The strong nuclear force is around 10, a 1, followed by 38 zeros, stronger than gravity. Okay, but our point here for today is this and this, the short range. If you can't read that clearly, I'm just going to rewrite this. This is 10 to the minus 35 meters. So an extremely short range, right? Now, what does this have to do with the gold foil experiment? Rutherford continued working on the um, gold foil experiment, and this is what he discovered. Essentially, I'm just gonna draw one gold atom here now. So this is the gold atom, and this is the nucleus. We don't really care about the electrons at this point because the range is so small that it doesn't really matter, right? So what Rutherford expected, so what I'm going to do is we're going to do the exact same thing. Again, I'm just going to simplify this just so it's easier for you to understand. The rest of this you can read up on your own, okay? I'm going to put it right there. Now, this thing, let's say that these things, I'm just going to draw the projected path if the gold nucleus wasn't there. So that's a projected path. Okay. Now I'm gonna draw with green the actual path followed. Now I'm gonna say that this particular distance is now 10 to the minus 30, let's just say minus 35, or even smaller, 36. And say, let's say that this distance is 10 to the minus 35, and then here to here is 10 to the minus 34. Again, not a very accurate description because of the scales, but this will work for now. Okay. Now, because of the nuclear range's short nature, what do you expect the top alpha particle to do? The top alpha particle will be expected to be deflected, going up there, like that. Okay. Similarly, this second alpha particle is also expected to be deflected, even more so, right? Because the closer the distances are, the bigger the force, whether it's attractive or repulsive. But here's the thing: if this thing, the third alpha particle, is energetic enough to overcome, so what's gonna happen is it kind of gets repelled until there. But here's the thing: this distance is still a close enough distance for the short force, or sorry, the strong force to act, right? So the strong force acts because of that very short distance. Rutherford got another surprise. This did that. So this is the evidence for the strong force that Rutherford discovered. Okay? And that, everybody, is what happened with Rutherford and his discoveries. All right, so we can end it here. All that's all I'm gonna end with. I'm not gonna give you exercises or anything. I'm just gonna hope that you all understood that, especially at least the first part. Okay. All right. So, all right, we'll end it. Before we end, I'm looking at the chat before we go. Okay, for the grade 8 and grade 12 students that I have, or even the guests. Yeah. Okay. So for the, I'll end the lesson right there. So, okay. Luigi, go ahead. Just tell me your question. I don't mind bad English. None of us here speak perfect English. Arya, your question first. Is the strong force gravitational? No, it's not. Okay, that's a good question. Let me go back there real quick. Um, you haven't learned this yet in your lessons, but basically, physics has discovered that all forces are four. There are four forces in nature, and those four forces are responsible for everything we know about the universe, including the forces that we exert onto each other. Okay. Uh, so first of all, we have gravity. We know what that is. We have the electromagnetic force. So the electromagnetic force, it's basically the force that keeps charges and magnets together, or they repel each other. So electromagnetic. Then we have the strong nuclear force. Okay. And then we have the weak nuclear force. Okay. The strong nuclear force is the force that keeps the nuclei, the protons in the nucleus together. Okay. And then for the weak nuclear force, it's the force that's responsible for making a neutron decay into a proton. Okay, random guy, will I give you time tomorrow to finish your PowerPoint? Of course not. I gave you a lot of time to finish that. Okay. Okay, let me get to the actual YouTube chat because it got lost in the. Okay, my chat stream here got lost, so let me get to YouTube real quick, and I'm gonna pause this so it doesn't feedback. Hold on. Because I saw an interesting question there earlier. Do you know how to like let me retrieve a feedback? Hold on. Okay, let's pause that. Do you have any idea how I can retrieve like a message in Twitch maybe? All right. Either way. All right. So here it is. Let me see the. I think the question was from. Hold on. Luigi. Okay, let me just see that. Rutherford is mainly found in physics. That's from director. Okay, here. How does Rutherford's experiment give a significant part towards today's science? Well, basically, if Rutherford wasn't, somebody would have discovered it eventually. It just so happened that Rutherford was the one who did the experiment, right? Um, Here's the thing. At that time, there were some physicists, and I personally didn't like this when I found out that this happened. But history being history, it is what it is, right? But for me, not for me. What happened was there was a time around this time that some physicists said that okay, we're really close to discovering everything, and there's no need for us to actually learn anything new. Then Rutherford and a few other people came up with their own experiments later on and proved that no, we didn't actually learn everything yet. Okay. All right. So because he didn't, because basically what's the idea here? They showed that we didn't really learn everything yet, so we just have to keep moving forward. And with that motion going forward, we discovered what are the scientific innovations that we got. We discovered how to make electricity. That's one. We discovered not discovered, but we learned how to harness radioactivity. And harnessing radioactivity gave us both nuclear power and nuclear weapons, right? So indirectly, Rutherford was responsible for the nuclear part because he discovered the nucleus, right? Also, Rutherford, there were other things that Rutherford did, but basically, his most significant discovery was that uh, this, the discovery of the nucleus. Okay, and this led us again to go further to study the atom further and discover new things about it. The other thing that leads into is the next model, which is the what's this? Which is the Bohr model. Okay, the Bohr model basically says a lot of things, but the Bohr model led us to understanding chemistry better. So without the Rutherford model, without Rutherford making his discovery, we would not have the Bohr model. We would not have chemistry as we know it now. So far-reaching, right? And another thing that Rutherford did, it's kind of related to the discovery of the nucleus again, is the discovery of the nucleus allowed us eventually to get into like quantum mechanics. And quantum mechanics is basically how we discovered to make electronic devices. Without quantum mechanics, we would not have the computers, the laptops, the cell phones, whatever devices you're using, we wouldn't have those. That you would, and we you wouldn't be watching me streaming right now. Okay, Fugo got a question. Gold foil was never tested. What things? Uh, that I have no idea, honestly speaking, because if the gold foil experiment is never done, we wouldn't have. But again, I really think that sooner or later, if it wasn't Rutherford, it could have been somebody else. Okay. Uh, okay. For this is something that I've kind of like observed. Okay. It's not. I'm just gonna say this now. It's not a knock on either culture, but I see a big difference between Western and Eastern cultures when it comes to naming stuff like this. Okay. So so okay. I'm going a bit to the side here, but the idea here is, have you ever noticed when something gets discovered in the West, it's discovered and then it's named after the discoverer, and then in the East, like China, India, Japan, what else? Arabia, that region. If something gets discovered, who gets the credit? The civilization, not the person. Think about it. It's okay. All right. How about push and pull? Is it included in gravity? Well, gravity is just a pull. All right. Uh, Gravity is just a pull, but every other force. Actually, no. Electromagnetism is a push or a pull. Okay. What else? The strong nuclear force is a push, definitely. No, sorry, it's a pull as well. And the weak nuclear force is, you can think of it as a pull, but it's not really a force in the traditional sense. Okay. Let's see the chat again. Push and pull. Okay. What things that currently would not exist? I like I said, for Fugo, going back to what Fugo said. So what wouldn't exist? I wouldn't know. However, I would still think that sooner or later somebody would have discovered it, and we still would have our things. Maybe just in a little bit later time. Asian scientists, they do, Luigi, they do. However, like I said, big discoveries are normally credited to who discovered them, right? And in the past 100 years or so, it's been Western scientists who had the big discoveries. So they were always named after after the Western scientists. It doesn't mean that the Eastern scientists or Asian scientists they don't do anything, but right now I think we're in the verge of making one major discovery, and I think that would be named after some Asian scientists soon. Okay. So they do. So going back to your question, do they play a big role in today's world? Yeah, they do, because even though they're not famous, they're still the ones working on different things, discovering newer, smaller details of those big things. Smaller details of those big things. And with those smaller details, we can actually progress further into the future, so to speak. Okay. Um, what's a good example here? Let me think. Okay. Most of the discover. Okay, let's just think of it this way. Modern physics. Okay, modern physics is mostly tied into what's this? Mostly tied into quantum mechanics or astrophysics. Most research is focused on those two big areas, right? And of course, all the big discoveries have been made, and most of those big discoveries were made again by Westerners. But who is making those small discoveries that are actually challenging the old discoveries? It's actually Asian scientists. Most of these Asian scientists work in international labs. It could be in Asia, it could be in the US, it could be in Europe, but big labs. They work all over the place. Right? So Asian scientists, even if they don't really have they don't get the credit like Western scientists do, they are always working and they're always contributing. Uh Not like that, Lionel. I'm talking about the big discoveries. For example, okay, I'll do a math one. Did you know? Here's a really good example. Who's familiar with the Fibonacci sequence? Even if by name only, even if you don't remember what it is. Okay? The Fibonacci sequence. We know it to be the Fibonacci sequence because the person who discovered discovered was Italian, European, right? But guess what? Indian mathematicians came up with that and also who was that? Chinese mathematicians also came up with that same idea way before Fibonacci. Way before. Yeah, lemon water, Jackie. Yeah, I'm a bit thirsty. Let me take a sip. Lemon water, not sponsored. Just saying it out there in case I get demonetized. All right. Lionel, I wouldn't say it's unfair really about that. It's just culture. It's just culture. So you have to take that into account. What did he do different? Nothing. Fibonacci did nothing different. He just discovered it at a later time, and he happened to be Italian. But there is proof that it's been discovered all over the world. The Arabs did it. The Indians or the Hindus did it. The Chinese did it way before Fibonacci. Okay, that's an example only. Okay. I see a debate on what's better on this drink. All right, this is the last question I'll answer on the stream because it's getting quite late, and my students, you still have some work to do for tomorrow. Okay, so this is the last question I'll answer. Okay, Fugo has another question. Okay, Fugo, the idea here, is what? There will be discoveries. In fact, I wouldn't say there will be. I'm gonna say there are. We're just waiting for experimental proof in terms of the sciences. We're waiting for experimental proof. Once the experimental proof is there, the theory is gonna be the next big thing. What's this theory in physics? This is a string theory. String theory. Okay. Uh, I'm not gonna go into the details, but string theory is basically this. Most of the things when we think of physics, we normally think when we see small things, we normally think particles. But if you go enough to a small enough scale, you'll see that those particles are actually little strings that are either single strings or looped strings. And if you look at it from the scale that we can only achieve, they look like particles. Now, why is that important? Because of the fact that if they are strings, then that means they can explain stuff that so far has evaded our best attempts. Now, everything is away with quantum mechanics. That's our current best theory. Everything's a wave and a particle at the same time. Okay? But the idea, Jackie, I'll talk to you tomorrow. I see that comment. Let's not do that. Let's be nice here. Okay. All right, but it's okay, Arya. At this point, you're still kind of trying to understand it, so it's okay. Yeah. But string theory again, it's been around for like what, 30 years, but we still don't have experimental proof. Okay, we don't have experimental proof for it. But once we do, that's gonna be our next big theory, and that's basically our next discovery, even though it's been around for so long. All right. So that's gonna be the last question I'm gonna answer on the stream. So for the grade 12 students, I hope I answered all your questions earlier. You can come ask me tomorrow in class or in school. Yeah. How do we experiment that? Uh, okay, how do you experiment that, Arya? That's the thing. We cannot, not at the moment. We cannot build a machine that's powerful enough to do it. We are currently trying to get to that level of power, but our closest thing is the Large Hadron Collider. We've discovered something with it, but still not string theory. Ah, all right. Okay, so it's good to help. Good to help everyone. All right. So with this, I think I'll end the stream here. All right. So before we go, remember if you haven't done so yet, especially the new ones, you can follow us on these channels. So YouTube, you can follow us on YouTube. You can follow us on Facebook. If I go live on Twitch as well, and I put shorts up in YouTube and and Instagram and TikTok. Yeah, on TikTok. So I put the shorts up there. So if you'd like to return to that, once it's there, you can see stuff. Okay. You can also check up the other stuff. So you can learn a bit more. All right. Oh, Jomok, nice to see you. Timor Leste. Ah, nice. Okay. All right. Bye, everyone. And I hope to see my students, see you tomorrow. For those in the live stream, see you on the next stream. Yeah. Okay. Bye, everyone. Live stream. The next live stream will be this Thursday, but I don't know what the topic is yet. All right. Anyway, so bye everyone. I'll see you on the next stream. You'll get a notification when the stream's gonna happen again. Okay, so I'll see you then. Till then, stay freaky, everyone. Bye bye now.